Welcome to the Field Engineer. Today we are talking with Richard Baker, the UK Engineering Manager, who works in the radiotherapy sector. Good morning, Richard. Can you tell us a little bit about your background, give us an introduction, where you started and where you've ended up so far today?
Hey Charlie, yeah, good to be chatting today. So where did I start? Well, I started at an early age, really, fixing stuff in my dad's garage, I was always out tinkering with things from as far as I can remember. That naturally led on to, push bikes, and then as you sort of mature, then motorbikes and cars, and just generally fixing stuff. So as far as I can remember back, I had an interest in engineering and how things worked. And then I bought a house, so thought, well, how does a house work? So then started doing a sort of learning about plumbing and electrical stuff. And I'm quite interested in the electrical side on cars and stuff. So I used to be an auto electrician. So I thought, how does a house electrics work? So I went to college and became a qualified electrician. And then did an electronics qualification and then mechanical engineering on after that. So that kind of gave me a bit of paper and some sort of grounding in what I was doing. And then I had various jobs fixing machines in factories and working in garages, rewiring cars and things like that. And then I found myself working in a hospital environment as started as an electrician, and then went on to start getting involved in more of the other sort of estate stuff. So became sort of an estates technician, looking after sort of heating, ventilation, water, alongside the electrical stuff.
Right.
So that's where it kind of all went a bit bonkers, because while I was doing the electrical stuff, I used to test the nurse call systems. So what I used to do was bring them back and test them, and I thought, well, I could make a little test box. So I made a little test box, and I was trying to get the electronic components. And the only place in the hospital that had components back in the day, was a radiotherapy workshop. So so I started going over there and getting resistors and transistors and bits and bobs and making these little circuits. Only sort of simple stuff. And that's when I first saw a LINAC, and my life's never been the same since.
And a LINAC is a linear accelerator, right?
So that's the shortened version down of the name of it. Yeah, so it's basically a linear particle accelerator. So you can imagine the thing at CERN that collides the particles, the 17-kilometer long thing. Yeah. It's just a sort of 1.5 meter, 2 meter long version of that. And yeah, so I was introduced to the LINACs, as we say, and haven't looked back since, really.
Mm-hmm. Excellent. Wow. So quite a journey. I guess, like a lot of engineers, you start at a young age tinkering and find yourself, going down that, route of fixing things, solving problems, and getting stuck in. So can you tell us a little bit more about the radiotherapy equipment? We've discussed in the past, how complex it is and all sorts of things. But could you give us, the audience a little bit of a 101 lesson on what radiotherapy equipment looks like and what it does?
Oh crikey, where do I start? So I started sweeping the floor. So I've learned these machines I'd like to think I've learned them from the inside out. It takes years to sort of get your head around how these things work, because there's so many different facets of it. But basically, let me try and condense it down into a very quick journey. So we start off our journey with a pulse forming network, which we call a modulator. So we take a 3-phase input, about 60 amps, and then we store that energy up in a bank of capacitors. So that energy gets turned into DC and stored in capacitors, and then pulsed off down to the machine. So if we think of terms of how much power is in that bank of capacitors when they're charged, it can be up to 33,000 volts DC at 150 amps. Wow. So that's enough power to run a small town. albeit for 3 millionths of a second. And then the pulse is discharged and it's gone. For those of you who are not electrically minded, you can think of it like a toilet cistern. Now, most people know how a toilet cistern works. So you have a small pipe coming in the house, small water pipe, and you fill up that tank full of water. And then when it's full up to the right level, it stops filling, and it will just sit there waiting until you've done your business, and then you need to get rid of it. And instead of, you couldn't flush all your business away with a small pipe, you have to have a great big of water. So we're doing exactly the same thing with electric. So we're storing the electric up, and then when we're ready, we flush that electric in a quick pulse down to the machine, the same as we do with a quick pulse of great big powerful water to get rid of our whatever we've been up to. So it's that's what the modulator does in simple terms. And then that pulse then goes down to either a klystron or a magnetron. Now those two bits of kit. For those of you who are on the video, there's a magnetron. For those of you who are driving and not able to see it, it's about 18 inches long, about 4 inches round. You've probably heard of a magnetron because it's in your microwave at home. So your microwave oven has a magnetron. So that big pulse of electric comes down to the magnetron. The one in your microwave at home does about 800,000 watts. The one I've just held up can do 5, 6, 7 million watts. So there's a little bit of a difference there, which is obviously why we need the great big power and the size difference. The klystrons work slightly differently, but they still produce microwaves up to 20 megawatts, 20 million watts. So if you do the math at about 20 megawatts and you sort of work out how long it takes to cook a chicken in a normal microwave, there's enough power to cook a chicken in about 3 seconds. Whether it work, whether you want to eat it or not, I don't know. Whether anybody's ever tried it. But yeah, so that's the kind of numbers we're talking. So we're still only a part way down the process. So we've got pulses of microwaves, and they're pulsing it up to 250 times a second. So it's quite a feat to get that much energy pulsing at 250 times a second. Where does those microwaves go? Well, they go down to what we call the accelerator. So this is the accelerating part. So this is the bit that's like CERN. So it's a copper tube, maybe 1.5 meters, 2 meters long, about 5 inches round, and it's under vacuum and it's full of cavities. So it's under quite a high vacuum, 10 to the -6 for those people who are in the know about that. And then what we do is that microwave energy then comes down and it fills up all those cavities in that copper tube. So we've now got a copper tube full of microwave energy. Then what we do is and again, for those of you who can't see, I'm holding it up, it's a glass container with a little coil, tungsten coil, about the size of your little fingernail. You can see in there. So that's what we call the electron gun. So basically what happens is that just sits on the end of the tube and just boils off electrons. So there's a little cloud of electrons just boiling off that coil. And then when all that microwave energy is in that accelerator, what we do is we put about 50,000 volts between this and the accelerator. And what it does, it injects those electrons into the end of that tube at 0.4 the speed of light. It's quite important. So what we've got now, a tube full of microwave energy, an electron gun on the end, and electrons then injected in at 0.4 the speed of light. Now, for those experts, we got traveling and standing waves, but the easiest way to explain it is on the traveling wave, it's the microwaves are like the waves on the sea, the electrons are like somebody on a surfboard. If you paddle out on your surfboard and you sit on the waves and you're just bobbing up and down, when a wave comes that you want to surf in on, you turn around and you paddle like crazy to try and catch the speed of the wave, don't you? And then the wave catches the surfboard and pushes the surfer in towards the sea. Well, that's what the microwaves do. They catch the electrons and then they accelerate the electrons, and the cavities in the accelerator expand back out. The microwaves then speed up and the electrons speed up. And then what we do is we speed the electrons up to just under the speed of light. So to give that some context, when the electrons come out the end of that tube, they'll go around the world 7 times in a second. So yeah, so then that's kind of what we're doing. And then what do we do with those electrons? Because the premise of the machine is to treat people's cancer cells, to damage the DNA in the cancer cells. So we need to get those electrons, or that radiation, down in towards the patient. So we have then a bunch of electromagnets, which then steer the electron beam. So any old timers or new timers that enjoy them, CRT, the old TVs, the old tubes,
cathode ray tubes. Yeah,
there we go. So basically an electron beam going down, and we steer the electron beam down towards the patient with sub-millimeter accuracy. And then we can either treat the cancer cells with the electrons, or we can turn the electrons into photons by slamming them into a tungsten target, and then we get photons, X-rays coming out the other side, and then those that radiation then goes down towards the patient. And I won't go into the patient side of it and all that stuff because we're talking engineering. But then basically what we do is we collimate that beam. So we have a beam of radiation down towards the patient, and what we want to do is then concentrate that beam into a precise area where the tumor is, or the cancer cells are that we want to mop up. So we use tungsten leaves. So we have about 120 tungsten leaves in the machine. So there's some leaves there. There's 2 leaves. And you can see them moving. So they're all independently moving. And the reason they move is because if I want to treat a circle with my radiation, and the easiest way to do it, remember, do you know these things? So for anybody driving again, these are the things you push up against a skirting board, and it gives you the profile of the skirting board with your plastic thing. So I've got 2 of them. So if we have a lot of tungsten leaves and we put them together, if that tungsten's blocking the radiation, then I get to treat just that little area in the middle there. And we can move those leaves because they're all independently driven by motor. We can move those leaves and change the shape of its treatment area. And like I said, that treatment area is sub-millimeter, and it's just, the precision is just wonderful. And they're like a work of art, those little things. So that's the premise of the machine. So we start off, bang, accelerate the electrons, lots of stuff happens in the meantime. Electrons come out towards the patient, we make them the right shape and the right energy, and then they do their work in the tumor.
Amazing, brilliant. That was a tour de force. That's an incredibly complex machine in the space of 5 minutes. So thanks very much, Richard. We've talked about you are finding it more and more difficult to get radiotherapy technicians and engineers, and I think you've given us a little bit of a flavor, but perhaps you can illuminate us a little bit more. What is the job of a radiotherapy technician engineer, and what makes it so worthwhile?
Like I said, I haven't looked back since I've seen the machines, and I've shown probably hundreds, maybe thousands of people the machines over the years, just working on a bit of equipment. If you take somebody who's an engineer and show them the inside of a radiotherapy machine and start explaining it, it's like nothing you've ever seen. It's just bonkers. And their eyes literally, like, you take an engineer or somebody who likes engineering in there, their eyes literally, like, and you can see their hands, they're like dribbling because it's just so amazing. It is, honestly, it's like, it's just another world. They're not, and every day is different. So there's so much stuff going on. I mean, I literally just I put my toe in the water there, and explained a little bit about the physics and stuff, but there's so much stuff going on inside these machines. And they're so big. So the gantry, so these machines are on gantries, they spin round. The gantry weighs between 6 and 7 tons. And to be accurate with a sub-millimeter accuracy is quite a feat of engineering, really, when you think of all the weight hanging on the bearing that the gantry spins around on. Yeah, just wonderful. Why wouldn't you want to work on something like that? I don't get it. I don't get it. But yeah, it's just
okay.
Yeah.
Brilliant. When you do hire engineers, when you're looking for the right people, what is it? What traits you're looking for? What are you looking for when hiring for these positions?
So that then becomes just as complicated as how the machine works.
Right.
Because as I described this, so you need to be a bit of everything. So you need to have electrical, high voltage, mechanical, fault finding, really have good fault finding skills, plumbing skills, there's water systems on the machine, heavy lifting. So you're lifting bits off the machine, it could weigh a good part of a ton. So you need to know how to do that. Particle physics. So you need to know a little bit about particle physics, what's going on there. Waveguides. So we have RF waveguides, microwave energy, electromagnetism, water treatment. So there, like I said, there's chillers and everything else, compressed gas. So we have a SF6 gas in the machine, which is the worst, or say it's the worst greenhouse gas you can get. So there's quite restrictions around that. The computer side of it just baffles me nowadays. It's changed so much in the time I've been involved in it. It's a really sort of, so there's quite a big sort of IT network inside. Radiation protection, health and safety. That's
something for everyone, right?
Yeah, and you need to. You could literally come in one day and have to reload software and start doing. We've been looking through log files last week because we had some issues, and then the next week you're coming in and you're pulling something that's a good part of a ton off the machine, and then trying to sort of get it all back on straight and sort of tweaking little bits inside the machine with your mechanical knowledge. And then the next day you could be, changing a water pump on the machine and having to bleed the water system. It really is like if you had a cheese board and it was engineering jobs, you just have every bit of cheese on there. It really is. It's not a day-to-day thing. It's every day's different, and every day is a school day. And I don't care how long you've been in radiotherapy engineering, there's always something to learn.
Yeah, I remember fairly recently speaking with Matt Neal, who I know you know, but he was, he'd been in the industry again a long time, and for him it was exactly the same. Every day it's something new, something different. Of course, there are some things you bring in knowledge and experience, but you're learning every day. And I think with that range of that range of different skills and different experiences, I think is an exciting thing. So, what would you say to any aspiring radiotherapy field service engineers? What would your message be?
Well, alongside all of those skills that you need to sort of fix the machine, we quite often have to turn up to situations where people are upset, patients are being phoned and saying, "Oh, your machine's down." So alongside all of those sort of engineering skills, one of the things that's just as important is the softer side of things and being able to deal with people, because it really is having to, we turn out that, it's quite regularly people in tears because the machine's if the machine's gone round and, done something it should, like we've had it where the machine's gone round and sort of just caught the couch and put a little hole in the couch, and that couch costs £30,000. So the rads are crying and, "Oh, I've damaged it and I'm going to be in trouble." So we have to come in and calm situations down, and so we quite often have to do a bit of counselling and that sort of thing alongside everything else. So that side of thing is really important, as well as fixing it. What would I? Well, just get, if you wanted to look at radiotherapy engineering, just start researching it and seeing how wonderful it is. But you really don't get you get a little flavour around the machines work, but this is much more than that. Anyone looking to get into it, it's not just turning up and fixing the machine and go in. There's a whole sort of relationship side. It's almost like you're a salesman and you're a diplomat and you're a counsellor, and so yeah, there's all this other stuff that goes into it that makes it. I think it makes it a little bit more special.
Sure. I mean, your passion, comes across, and Yeah,
Sorry.
we in the prep meeting for this, we spent a good long hour chatting over the technology and the people involved. So yeah, again, you said to people, get involved, go and find out about this stuff. Are there any networks or other resources where people can go and find out about this stuff and talk to people? What would you recommend?
Yeah, so I mean, if you're looking to get into the profession, then I would keep an eye on job sites. Mainly, so there's three different sort of models that we do. There's the in-house model, so the where the engineers are based at one site at a hospital. The model that I currently manage is like a remote model, so we've got engineers that kind of fly in and fix, but they have the sites at thing. And then there's the manufacturer model, so the manufacturer will then send their engineers in to fix it. So we have the three models, the in-house, the third party, and then the manufacturer. So when looking for jobs, NHS websites are, NHS jobs, and all they usually go out to these other places, Indeed and whatever. Oh, sorry, I didn't know if I was meant to mention that.
It's fine.
Yeah, so other job sites are available. So yeah, just normal job sites, and then keep an eye on the manufacturer stuff. So again, you can research the manufacturers. There are jobs that come up, but the training involved is quite intense. So it's not just a sort of you pick it up in a couple of weeks. It takes a long time to be able to be sort of proficient and be allowed to be on your own.
Safe.
Well, and that's it exactly, because there's so much stuff that you so don't come in expecting to think, oh, I'm gonna I'll be a radiotherapy engineer in three minutes, because it won't be like that. As good as you are, it's still going to take time to get used to the machines. No matter how good an engineer you are, you can't just come in. You need to have that sort of familiarity, because there's so much stuff around the machines, and so much stuff relies on, you could do a little tweak at one end of the machine and it can completely throw it at the other end, because everything relies on, all the microwave energies and electrons, and everything's just relying on everything just so precisely. So yeah, it's a massively, like, the career is just, I would recommend it to anybody, because I mean, I might be a bit biased, but you get to work on, like, for me, I'm working on some of the coolest machines in the world, and it's like having that lovely cake, but then there's a cherry on the top, which is that you're saving people's lives.
Yeah.
And I don't think an engineering job gets much better than that.
Yeah,
but I
wholeheartedly agree. Excellent. Richard, thank you very much for your time today. It's been a really interesting conversation, so thank you very much. To our viewers and listeners, if you have any questions, if you have any experience of radiotherapy, either as a patient or as an engineer, if you wish to share that with us, then please do get in touch. And otherwise, I will say thanks again to Richard and the audience, and we'll see you again on the next one.
Thanks, Charlie.
Thank you.